Wow, now that is interesting. Hi, didn't see you there. I'm Mr. French, your AP Stats teacher. I've been looking for an opportunity to make another video for you folks, and looks like I found it. Today, I'm going to introduce to you the concept of a chi-squared goodness of fit test statistic. So why don't you follow me, and let's get started on chapter 11.1, day 1. So welcome to your lesson on a chi-squared goodness of fit test. The goals for this unit, well, the goals for this section is to state appropriate hypotheses and compute expected counts for a chi-square goodness of fit test, and also calculate the chi-squared statistic, degrees of freedom, and a p-value for a chi-squared goodness of fit test. All these ideas should sound familiar except for the idea of a chi-squared goodness of fit test. Okay, so in the M&M example that we did today in class, okay, there is some sort of claimed distribution or assumed distribution. So with the goodness of fit test, there's always some sort of claimed or assumed distribution by either a company or there's some other circumstances. So for example, I think one of your homework problems says that, like, you know, the birthdays of hockey players, are they equally distributed? And so we assume that they are equally distributed throughout the year until there's evidence to support otherwise. But in a goodness of fit test, there's always some sort of claimed or assumed distribution. And so we're testing to see how good a distribution fits on a set of data. So let's see an example just for a second to show you how a chi-squared test is different than your regular old like proportion significance test. So like in our example today, let's say that we had something like this. So let's say that we had a distribution of, you know, blue, orange, green, and all the colors. So let's say in our example today with the M&Ms, we had this distribution here. So we have all the colors here. We have our total, and then we counted, so like we got a bag of 60 M&Ms, and we saw something like this. We got like 9, 8, 12, 15, 10, and 6. We have a total of 60. Let's just take a look at what happened to the blue proportion here. So our sample proportion for blue, I'll say, is p hat equals 9 out of 60, which is equal to 0.15. Well, it turns out that the company's claim was that the proportion for blue is set at 0.24, at 24%. So obviously we have evidence to suggest that that may not be the case because this is less than what the company claimed. We could use a one sample z-test for this particular color, but then we'd have to do the same thing. So we would assume it's 0.24. Here's our p hat, we would use a z-score. We could do a one sample z-test for a proportion on every single sample proportion that we got and compare it to its claimed value. That's technically one way to do it, but in this case here we'd have to do 6 of those, which is where a goodness of fit test, a chi-squared goodness of fit test, it becomes very much in handy. In a chi-squared goodness of fit, it would look something like this. In the M&M example, what we do is we assume that a distribution is true. Your null for the M&M example could look something like this, and it would be really long, but technically this would work. You could say that the null is that the proportion of brown is 13, the proportion of red is 13%, the proportion of yellow is 14%. So this is the company's claim distribution. And then your alternative would have to be something like at least 2 of these are not equal to each other, which honestly, in a goodness of fit test, there's actually a much easier way. So once again, the null is the assumed hypothesis. It's the dullest one, so we're going to assume that the company is telling the truth. This is one way you could do it, but honestly, I do not recommend it, ever. So I'm going to say, or you could simply say this. This is how I'd like you to set up your null and alternative hypotheses for a goodness of fit test. Check this out. We can just write it out in words. We could say, our null hypothesis is the company's stated color distribution for all M&M milk chocolate candies is correct. And I bet some of you are thinking, wait, does that mean that the alternative is simply that it's incorrect? And you'd be right. This is what you could write for a goodness of fit test, because we're doing a significance test on a distribution of numbers. Your null is simply kind of stating with the context, baby, that the company's stated color distribution for all M&Ms is correct. Alternatively, the company's stated color distribution for all M&Ms, milk chocolate candies, is incorrect. And the big thing here is the word distribution. We're doing a significance test on a distribution of numbers, not just one number, but a distribution of numbers. Okay, so let's take a look at an example of how to create one of these test statistics. So this is the claim. Now let's say that I go out and I buy a bag of candies, or I get a random selection of candies. I actually simulated this using my random number generator to see what would actually happen, and I got some interesting results. So I simulated picking a bag of M&M candies with this proportion of each color, and what I got was this, my observed counts. In my sample of 60, I got, surprisingly, I got 15 brown, 7 red, 9 yellow, 4 green, 9 orange, and 16 blue. So I did a quick simulation. So I said that the numbers 1 to 13 represent brown, the numbers 14 to such and such, 14 to 26 represent red, 27 to 40 represent yellow. So I essentially randomized, let me show you my little scratch work here. I set these numbers to be these colors, and then I randomly selected, using my random number generator on my calculator, 60 numbers from 1 to 100 to simulate what would happen if this was true. And I got this sample. Okay. So the observed is just what happened in your sample. Then there's this thing called the expected counts. Well, the expected counts essentially are using this proportion with your sample size and just finding out what proportion of your sample size. So like if this is the true proportion, this is your sample size, we're going to take 13% of 60 to get our expected counts. And I have those here. One thing with your expected counts, always keep those decimals. I know it sounds counterintuitive, but keep the decimals on your expected counts always. Because these expected counts are what should happen on average, and averages can certainly be decimals. So our expected counts, 7.8, 7.8, 8.4, 9.6, 12, 14.4, and it turns out if you add these up, you still get 60. But I'm getting these numbers from using the proportion of what they claimed. So that's how you calculate the expected counts. So now, let's talk about the chi-squared test statistic. There is a formula in your formula sheet that you do not have to memorize, which is really nice. We talked about it yesterday in class. The chi-squared test statistic looks like this. You take all the observed counts minus the expected, and you square those differences. Why squaring? Because that makes all the differences positive, and we don't like it when negative differences and positive differences cancel themselves out. Then we divide each of these squared differences by the expected. If there's time at the end of the video, I'd like to justify why, what the reasoning is behind this. It's kind of interesting. And then we take each of these calculations and we just simply add them all up. And this gives you, this is going to equal your chi-squared test statistic. So chi, this is actually the Greek word for x, so they call it chi. We like to use Greek letters in statistics a lot. In this example here, let me show you what the work involved. So this is the work that you would need to show. If you ever, when you calculate a chi-squared test statistic, this is how you calculate it. So what we do is we take the observed minus expected squared divided by the expected. And it looks a little bit tedious, but I'll show you a shortcut. So it looks something like this. So this is the long way to write it out. Our chi-squared is equal to the observed count. So let me show you here. The observed count here of 15. Zoom out just a touch. So the observed count here of 15 corresponds to this. So 15 minus 7.8 squared over 7.8. And then you do the same thing here. 7 minus 7.8 squared over 7.8 for every single one. I ran out of space here. It's a little tedious. Kind of shove that down there. It turns out you don't need to do this. And you're going to see some examples of, well, I guess I shouldn't say that. You won't need to write every single thing out. It turns out on your assessments, it is completely reasonable to write like the first two terms. As long as you put a dot, dot, dot. So if you write the first two terms and put a dot, 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 and then give us the value, then you're good to go. It turns out that value is 10.97. So this is the amount of work that you would need to show. Let me show you what it looks like on a calculator. You can do this. So for some folks with their calculator work, they're like, oh my goodness, this is going to be ridiculous if I have to do this all the time. There's a way you can do this on your calculator, and you can kind of do this in the background, especially if you just write dot, dot, dot. You can jump to your calculator and have it give it all to you. So check this out. If you go to your calculator, and I go to Stat Edit. Now, I've done something kind of weird. If you zoom in, oh, you can't zoom in too much further, can you? Hang on. Yeah, you can. I can bring the camera a little bit closer. Okay, check this out. So I've put my observed counts in L2 and my expected in L3 for some reason, because this is my M&M collecting data here, so don't worry about that too much. I have observed in L2 and expected in L3. Now here's the cool part. If you click the stat button, you click the stat button and you go over to tests and you scroll down all the way to chi-squared GOF test. If you click enter, as long as you put your observed counts and your expected counts in the right spot here, degree of freedom. So we haven't talked about that yet. Let's talk about it right now. The degree of freedom for a chi-squared goodness of fit. Degree of freedom for a chi-squared test, goodness of fit, is the number of categories. Some of you may be expecting it. -1. And so in this case here we had 6 colors. So our degrees of freedom for this particular test is 5. Mr. French, why is it like that? Well, the answer is beyond the scope of this class. We're just going to leave it at that. So, that's a really important idea. Degree of freedom in this case, there were 6 color in our category, so we have degree of freedom of 5. And I'm just going to calculate it. There's our degree of freedom. Or sorry, there's our chi-squared, and we actually get a p-value as well. What? Yeah, we get a p-value. It's super cool. This contribution, you should know what this contribution is, and it's going to ask you like which thing is contributing more to this test statistic. Contribution, if I kind of scroll over, it shows me different numbers. Check this out. The contribution, the CNTRB, tells you the value of each of these sums. So like it's telling me that like this number here, 6.646. This one here is 0.0820. This one here is 0.042. So what the contribution tells you is like which category is like increasing your chi-squared the most. So for example, like if your observed minus expected is close to 0, then that means that this is fitting pretty well. So this has a low contribution. This is close. I mean, if it was a perfect match, this would be 0. So we say that this has a low contribution. It's not contributing that much to overall test statistic of 10.97. This is not contributing that much. This contributes a lot more because it's further away from its expected. So it should, we shouldn't be surprised that this contribution is 6.6. So that just means that this is has a higher contribution. It's contributing a lot more to this. And so, for example, we may investigate further on the highest contributing factor. Like this is matching pretty well, but it depends on the case, it depends on the scenario, but there's potentially something fishy going on with the brown M&M colors here. This is brown, this is red, so red's matching pretty well, brown's not matching too well. And then this is the yellow contribution. Yellow contribution is matching really well. We observed at 9, it was supposed to be 8.4, so it's doing a good job. So it just kind of gives us an eye for what we should be mindful for, especially if we want to do like a follow-up study. We might want to do a follow-up study on the highest contributing category to this test statistic. So now here's a question that I posed towards the end of class, I believe. How crazy is this type of score? With a z-score, if we had a z-score of 10, if our z-score was 10, we would have a very small p-value. We'd be way off in the tail of our distribution. But how are chi-squareds distributed? So I will attempt to show you on my computer screen. So let's check this out. Okay, so this is going to be kind of crazy. I've never done anything like this before. So what I have here is a simulation. I'm filming my computer screen right now. I hope you can hear me because my shotgun mic is facing this way. So what I have here is, check this out. I have a null. So this is, dang it. Wow. That feeling when your null hypothesis doesn't match up what you wanted it to be. Alright, lights off. It's a little bit crazy, but I'm going to show you how chi-square distributions are distributed. So here's my null hypothesis. Okay, so it's under the assumption that the distribution of these colors match. Yes, 13%, 13%, 40%, 16, 20, 24. So this was our original sample. This is the sample that I generated. Oh my goodness. This is the sample that I generated. Okay. So we have a sample size of n equals 60. And we have a chi-squared of about 10-ish. It's not exactly the same. That's okay. So check this out. I'm going to see where this distribution, where this chi-squared lies, if we were to do this sampling over and over and over again, if we were to get a bunch of M&Ms, a bunch of 60 M&Ms, so let's watch what happens here. So I'm going to generate one sample. Generated it, and there it is. Come on. There's the sample. Okay, so that is, I just got some candies, there's 60 of them, and it did that whole long convoluted thing. It did a goodness of fit, it calculated a chi-squared with the same expected counts, but now compared to these observed, and you see that I get a chi-squared of 5.11. Okay, and so that's plotted right here, 5.11. So I'm going to do it again. I'll just show you. Okay, getting another sample in 3, 2, 1. So there's the next sample, and I got a chi-squared of 10.255. So I've just done another sample of 60 candies, and I would do observed. These are the new observed, and then minus all the same expected. So we always expect the same. That should make sense. Out of 60, I'll generate it again. 7.4, 4.2, and so I'm getting a bunch of distributions. I'm getting a lot of chi-squares under the assumption that the claim distribution is true. So I'm getting a bunch of M&M candies. And I'm doing this over and over and over again. Keep track of those chi-squared values. This is really exciting. Okay, here's the big reveal. Check it. Here's a dot plot of all those chi-squared values. I'll generate 10 more now. 10 more, 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 10 more. I know some of you are like, oh, it's going to be a normal curve. Oh. Notice how these numbers here go from 0. That should make sense. Think about it. If the observed minus expected were all the same, this is perfect. So in this case here, a perfect chi-squared is 0. That means all the observed matched all the expected. Okay. And I'm going to generate now 100 samples. Zoom out. Holy smokes, we got like Old Faithful over here. Let's generate 1,000 samples. And we get a very beautiful curve. And it is certainly skew right. Fantastic. Chi-square distributions are always skew right. This is a really nice curve. Super cool. So now this, look, we've done a looks like 14,000 samples of M&M candies. So this was the observation. This is what we observed. This is what I actually did. And this is what happens in the long run. And so we could ask the question, you know, we got about 10. So is 10 super, super rare? Doesn't seem that rare-ish. How rare is it? Well, that's a p-value. Oops, oh my goodness, I thought I was recording on the computer. That is how the chi-square distribution is distributed for different degrees of freedom. Very similar to the t-distribution, it needs different degrees of freedom. So our degree of freedom is always the number of categories minus 1 for a goodness of fit test. There are 3 types of chi-squared tests. This is the first one, goodness of fit. So now the question is, how can we calculate a p-value? So we have our test statistic, 10.97. We have our degree of freedom. So if we go to the last table, holy smokes, it's been a ride with you folks. It's been such a great time. Look at this. So this is the chi-squared table. It's the very last one. Oh, we made it. As we go on, we remember all the probability tables that we had to be able to read. So our degree of freedom line is 5. Degree of freedom is 5, so that's right here. We had about 10.9, I think. Yeah, 10.97. So here's 5, and our chi-squared is 10.97, which is located somewhere in here. And we read it very similar to a t-table. So if 10.97 is somewhere in here, our p-value would be somewhere in here. Okay, so it's above 5%. Below 10%, above 5. So one way you can get a range is by using your table, but honestly, you're going to be using a lot of calculators in this chapter. And so one thing that you could do, you take a look at here, is your calculator tells you your p-value right there. You know, we said it was between 5 and 10%, and sure enough, there it is. It's right here, 0.052. So our p-value is 0.052. This is what your objective is today. Your objective, your practice that I want you to do, is the first thing you're going to do. So now, now that you've seen all this stuff, feel free to take a look in the book, the first part of 1.1. We haven't done the full significance test. We're going to wait for next week to carry out a full significance test because there's different conditions that need to be met. But I would like you to do suggested practice now. So work on the suggested practice. 11.1 suggested practice. Questions 1, 3, and 5. If you get done early, I'll assign some cons. If you're good to go on that, and you want some more practice this weekend, take a look at the check your understanding. If you want more practice, if you really want to get a good idea, the even ones after this are pretty much the same types of questions. So if you do 2, 4, and 6, that would also be an option for you. And that's kind of nice because the answer key is not given to you. You can come and ask me after class someday. So let's revisit our goals. Our goals were to state the appropriate hypotheses and compute expected counts for a chi-squared goodness of fit test. So we did that. Remember, when you state hypotheses, just say the company's, essentially you're saying, let's just assume the company's claim is true. Alternatively, it's not true. Or if the company's claim is correct, or the company's claim is incorrect. But you'd make sure that you elaborate, give context on what company that is. And calculate the chi-squared statistic. So that is the formula that we looked at. Degrees of freedom is number of categories minus 1. And the p-value for a chi-squared goodness of fit test, that can be found from the table, or you can use technology. This has been a great time. Wow, that sure was fun. I hope you had a good time learning about the chi-squared goodness of fit test. So, I'm excited to potentially be making more of these videos for you. Have a good rest of your day and have a great 3-day weekend. Wow.